Welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we are doing a deep dive into Unit 2, electrostatic potential and capacitance. And we're going to tackle a concept that often causes a bit of trouble, the electric potential of an electric dipole. Our goal is pretty simple, actually. We want to figure out why two opposite charges, when they're sitting really close together, create an electrical effect that's so different from a single charge. If a single charge's influence fades as 1 by r, why does a dipole's effect just vanish so much faster? So let's start with a simple real-world question. We all know a water molecule is basically an electric dipole, right? It has a slightly positive side and a slightly negative side. Now imagine you have two of these water molecules and you place them far apart. Do you think their electrical influence on each other would drop off quickly or slowly? And more importantly, is there a spot somewhere near them where their influence just completely disappears?
That's actually a bit confusing. My first thought would be that, since a dipole has two charges, its effect should be quite strong, maybe even stronger than a single charge if you're close enough. How can two charges end up being weaker than one?
And that is the exact counterintuitive point that trips everyone up in the exam. The key thing we need to get today is that for a dipole, the positive and negative influences, they almost perfectly cancel each other out as you move away. This cancellation is what makes the whole effect decay so rapidly.
Okay, so cancellation is happening. But if they're canceling out, then shouldn't the electric field also be zero? I mean, the force that pushes a test charge. If the potential is balanced, the forces should also balance out, shouldn't they?
Now this is where the physics gets really interesting. The surprising thing is, there's an entire plane in space, the one that cuts right through the middle of the dipole, where the electric potential is exactly zero. But, and listen carefully, the electric field there is definitely not zero. So we need to understand how the potential can be zero while the force is still very much active. Okay, so let's unpack the core idea. At its heart, a dipole is just a system of two charges, plus q and minus q, separated by a tiny distance, which we call 2a. The potential at any point p outside this system is just found by applying the superposition principle.
Superposition. So we just find the potential from the positive charge V plus and the potential from the negative charge V minus, and then we just add them up.
Exactly. And this is the crucial point. Potential is a scalar. It's like money. Positive potential is like having money. Negative potential is like a debt. You just add them algebraically, with their signs. So the positive charge gives a positive potential, and the negative one gives a negative potential. They're designed to fight each other. Now, if you are very far away from this dipole, the distance to the positive charge, let's call it R1, and the distance to the negative charge, R2, are almost equal. Not perfectly, but almost. So the positive potential and the negative potential are almost equal in size. And when you add a positive number and a nearly identical negative number, what do you get?
Something very, very close to zero.
Precisely. The result is tiny. And that's why the potential fades so quickly.
So the secret is really that V is a scalar quantity. If it were a vector, like the electric field, they wouldn't just cancel. They would add up directionally, maybe giving some sideways force. But potential has to cancel because of the signs.
You've absolutely hit the nail on the head. That scalar nature is the key. It forces an algebraic cancellation that just doesn't happen with the vector electric field. To give you a mental picture, imagine two sources very close to each other. One is like a bright lamp emitting light, which is our positive potential. The other is like a black hole, sucking in light, emitting darkness, our negative potential. Now, if you stand very far away and look at this pair, what do you see?
I guess they would just blur together. The light and the darkness would sort of neutralize each other, and it would all just look gray, a very low contrast gray.
That gray is our zero potential. It's the same idea behind the bar magnet analogy. A magnet has a north pole and a south pole. Close up, it's strong. But far away, its influence becomes very weak, because the two poles cancel each other out. And look, this idea of cancellation isn't just for exams, it's fundamental. It's how molecular interactions work. Think about why water is called the universal solvent.
Because it's a dipole?
Exactly. It dissolves salt, NaCl, because its positive end can pull on the negative chloride ion, and its negative end pulls on the positive sodium ion. It literally tears them apart.
Oh, so that small separation of charge gives it the power to break other bonds? That's actually very cool.
It is. And another thing, microwave ovens. They work by sending out microwaves tuned to the exact frequency needed to make the water dipoles in your food flip back and forth very, very fast.
And that flipping creates friction, which is heat.
You got it. If water wasn't a dipole, your microwave would be useless. Okay, so we have the core concept now. Cancellation. Now, let's see how Inser thermally defines this. Can you read out the formula for the potential far away from the dipole?
Okay, I have it here. NSERT says, for points far away, the electric potential of a dipole is approximately given by V equals 1 upon 4 pi epsilon naught times P cos theta upon R squared. And it says this is true for distances are much, much greater than the separation A.
Great. Now, looking at that formula, two big questions should pop into your head immediately. First, why does a scalar potential depend on an angle, theta? Direction shouldn't matter, right?
And second, why is it 1 upon R squared? Every other potential we've studied, for a point charge, a shell, a wire, it's always 1 upon R. Why is the dipole the only one that breaks this rule?
That 1 upon R squared is the real mystery, isn't it? Let's build it up logically, without getting lost in the maths. Remember, the total potential is V plus V minus, which is basically a subtraction, because V minus is negative. So we are calculating the difference between the two potentials. If we were infinitely far away, the distances R1 and R2 would be identical, and the potential would be 0. But we are just very far away. So there's a tiny, tiny difference between R1 and R2. And when you do the maths, when you subtract 1 upon R2 from 1 upon R1, the final result is no longer proportional to 1 by R. Because R is so large, that small difference between the two terms, it actually becomes proportional to 1 by R squared.
So it's the difference between two 1 by R terms that results in a 1 by R squared decay. The cancellation makes it die off much faster.
Exactly. The influence dies off as the square of the distance. And that cos theta term, that just tells you how effective the cancellation is at your location. If you're on the axis, theta is 0, cos theta is 1. The cancellation is least effective, so potential is maximum.
And if you're on the perpendicular line, theta is 90 degrees, cos theta is 0, so the potential is 0. The cancellation is perfect.
Perfect. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. So let's use that formula for a quick check. That surprising fact about the zero potential plane. If we take a point on the equatorial line, the line that is perpendicular to the dipole axis, what is the angle theta?
The equatorial line is the perpendicular bisector, so the angle between the position vector and the dipole axis has to be 90 degrees.
Correct. Now plug theta equals 90 degrees into our formula. What happens?
Well, plug theta becomes 0, so the whole numerator becomes 0, which means V is 0. The electric potential is 0 everywhere on that line. It works.
It does. And zero potential means zero work is done if you move a charge along that entire plane. You're basically moving in a neutral zone. And understanding this is so important because this whole idea of microscopic dipoles is what leads us directly to our next big topic, dielectrics. A dielectric is just a material full of these tiny dipoles, and knowing how their potentials add up is the key to understanding capacitors. All right, now this is important. Let's talk about the silent killers. The two key misconceptions that steal marks on this topic every single year. Misconception number 1. The wrong idea is that dipole potential falls as 1 by R. Students just memorize the point charge formula and apply it everywhere. The correct idea, because of that powerful cancellation, is that it falls much faster as 1 by R squared.
Okay, so I need to remember that the cancellation acts like a huge brake, making the potential just vanish much more quickly as you move away.
Exactly. Now for misconception number 2, which is even more dangerous, the zero potential confusion. The wrong idea is thinking that wherever potential V is 0, the electric field E must also be 0.
Right, confusing the scalar with the vector.
Precisely. Remember our analogy. Potential is the hill, field is the slope. On the equatorial plane, the potential V is 0. That means the height of the electric hill is at ground level. But the ground can still be sloped, right? There can still be a slope even at 0 height.
So the slope, the field, is not 0. Okay, let me try to rephrase. On the equatorial plane, the potential energies from the positive and negative charges balance out perfectly to give V equals 0. But the forces, being vectors, don't cancel completely. They just add up to give a net sideways push or pull.
You've got it. That's precisely right. The forces add up vectorially, creating a net field that actually points opposite to the dipole moment. Forgetting that distinction is a guaranteed way to lose marks. So to make sure this all sticks, let's use a couple of memory aids. First, for the decay rate, a simple phrase, dipoles die doubles. The influence falls off as the square of the distance, R squared, doubles.
Dipoles die double. Okay, I like that.
Second, a physical gesture for the V equals 0, E not equals 0 situation. Hold your arms out straight to the sides, horizontally. They represent the positive and negative charges. Now that invisible line that runs perpendicular to your body right through the middle, that's the equatorial plane.
Okay.
That central line is neutral. V is 0. But you can feel the tension, right? If you put a charge there, it would still feel a force pulling it in or pushing it out. The field, E is definitely there.
Right. The slope is still present even if the height is 0.
Got it. Always keep that image in mind. Now, let's wrap this up with 3 factual bullet points that you must remember for the exam. 1. At large distances, the electric potential of a dipole is proportional to 1 by r squared. It decays much faster than a single charge's potential. 2. The potential depends on the angle theta between the dipole moment vector p and the position vector r, specifically on cos theta. And 3. The electric potential is 0 everywhere on the equatorial plane, where theta equals 90 degrees. But the electric field on that plane is non-zero. To get maximum marks in crystal clear concept clarity in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, ProfSam.com. Thank you for joining us for this deep dive. Now, just one final thought to leave you with. We saw that a single point charge potential goes as 1 by r, and a dipole goes as 1 by r squared because of that plus-minus cancellation. So what if you arranged 4 charges, 2 positive and 2 negative, into something called an electric quadrupole? The cancellation would be even more effective. What do you think the potential would be proportional to then? Maybe 1 by r cubed. Think about it. We'll explore that next time.